Hi everyone, welcome back to disinfection and sterilization. I'm making this video lecture today because yesterday I canceled class due to the heat wave. So today we're going to be looking over other sterilization methods aside from steam, hydrogen peroxide, anything that we've already looked over, quality assurance monitoring, and chemical indicators. So another method used for sterilization is dry heat. It operates without moisture and uses high temperatures to sterilize instruments. Unlike steam sterilization, which uses moist heat, and convection, dry heat uses conduction. So that means heat travels molecule by molecule to reach the item's core. This is effective for materials that can't tolerate moisture, such as powders, oils, greases, and certain metal instruments. It requires longer exposure times and higher temperatures, often around 160 to 170 degrees Celsius for 2 hours. While it's effective, it's not commonly used in the MDRD because of the time involved, risk of heat damage, and limited versatility. So it's more used in labs. So conduction versus convection, what's the difference? Conduction involves heat transfer through direct contact, where each molecule passes energy to the next, while convection used in steam sterilization involves circulating hot air or steam to transfer heat. Understanding this helps explain why dry heat sterilization takes longer. Conduction is slower but more direct. All right. So dry heat sterilizers are excellent for materials that can't handle moisture. It's best for glassware and items like microscope slides. It avoids water residue and keeps items looking clean and clear. However, it requires high temperatures, which can damage items like rubber or ointments. Also, the longer cycles increase the risk of operator error. This enforces why MDRDs don't usually use this method. So advantages include suitability for glassware, as I mentioned, no water spotting, and preserving appearance. But limitations include incompatibility with other sensitive materials, extended cycle times, and higher risk of user mistakes as a result. You always have to weigh the pros and cons depending on the material being sterilized. So we have different kinds of heat sterilizers, dry heat sterilizers, that is. So gravity convection ovens rely on natural air movement. So, the usual hot air rises, cool air sinks, slower heat up and sterilization times as a result of this. Heat distribution may be less uniform, especially in large loads. It's commonly used in basic lab settings or non-clinical critical applications. Fewer moving parts means lower maintenance, but of course it reduces the efficiency as well. And then we have mechanical forced air oven. It uses an internal fan to actively circulate hot air. It provides faster and more uniform heat distribution as a result. So it's more efficient at maintaining consistent temperatures. It's ideal for validated sterilization cycles in critical instruments. It's often required by manufacturer IFUs. And as a result of the actual internal fans, this means that it does have more maintenance as a result, but of course it has an increased efficiency. So proper use of dry heat sterilizers. So you have to follow strict loading protocols. Load items with space between the items to allow hot air to circulate. You have to make sure not to overpack. This can block airflow and cause cold spots. You have to use metal trays or open containers that withstand high temperatures. So you have to avoid plastic or rubber items. since most are not heat resistant. You have to ensure correct cycle parameters. So verify that time and temperature match device and IFU requirements. So for example, you have to have it set to 160 degrees Celsius for 120 minutes or 170 degrees Celsius for 60 minutes. So the higher the temperature, the lower your time is, because the longer you put items in there, even if it's not, sorry, even if it is heat resistant, the longer it is exposed to such high heat, the more likely it will uh, warp or slowly loses its integrity. So as a result of this, it's not used in MDRDs. These units are more common in research labs or industrial applications. It's still tested on the certificate exams for MDR programs, since it's pretty useful to have this theoretical knowledge. So packaging materials for dry heat. So you have to use only heat resistance materials like stainless steel, glass petri dishes or flasks, heavy duty sterilization wraps. Avoid plastic pouches or packs meant for steam, since these will melt. So obviously you can't put these in here since they'll more likely be set on fire. So you have to use packaging that allows heat to penetrate and keep items sterile after the cycle. So items like batteries and plastic cheek retractors like this, these will not be properly sterilized in the dry heat method. Chances are they will break down and no longer be usable as a result. So common containers and wrapping techniques. So since we rely on heat conduction in dry heat sterilization, so we don't rely on airflow or penetration like steam or gas sterilizers, we have to use packaging materials that allow heat to transfer effectively. So metal canisters and glass jars are ideal because they conduct heat well, even with lids on. The heat travels through the container to sterilize the contents. Aluminum foil is also common, so a lot of the peel packs that are used in dry heat methods are actually made out of foil like this. It's heat resistant and wraps tightly without blocking heat transfer. So we avoid paper, plastic, or steam pouches here. They can't handle high heat and don't allow proper conduction. So even if the peel pouch, for some reason, it actually manages to stay intact during a dry heat cycle, chances are the instrument inside or material inside were not properly sterilized, because the way dry heat works is by contact. So the key is choosing materials that let heat move directly into the instruments to ensure effective sterilization. So this here is the actual external chemical indicator used for dry heat. So when it reaches a certain heat temperature, the color on this tape will change to this. And now moving on to gamma irradiation sterilization. So this is a high-tech industrial sterilization method used more commonly in manufacturing. It employs gamma rays, so that's high energy electromagnetic waves from sources like cobalt-60. It penetrates packaging and product surfaces, making it ideal for disposable syringes, sutures, implants, gloves in sealed pouches, but due to the cost of gamma irradiation sterilization, radiation safety concerns, and just the general infrastructure needed for it, it's not used in hospitals. It's more used by manufacturers for mass sterilization. So it's similar in a way to ETO sterilization. So this is what they would use when sterilizing disposable instruments that are being sent to hospitals, such as custom packs, for example. And this is a common thing you will find in disposable items. Not so much this method. I rarely see disposable items have this symbol. More common ones are ethylene oxide and irradiation. And if you're to look at this suture, it says sterile R. So this was sterilized by irradiation. So sterility assurance overview. It's a system that confirms devices are reliably sterilized. It includes installation commissioning. So you ask questions like, oh, is this equipment installed correctly during this part? And we also have operational qualification. So does it work according to specification? Does this thing do what it's supposed to do? As exactly as is intended or required. And we also have performance qualifications. So can it sterilize actual loads? These checks are mandated by standards. So that's CSA Z314 to maintain consistency, safety, and accountability in healthcare settings. So the first step is installation commissioning. So it's performed by the manufacturer certified technicians. This process validates that the sterilizer is installed as per specification. It checks utility systems like the water, steam, drainage within the hospital infrastructure. It verifies environmental compliance, so that's clearances, ventilation, any electricals, confirms documentation of safety and function prior to use. So this is the foundation for all future validation steps. So hospitals must assign qualified staff to oversee the installation. They have to maintain purchase and installation records, confirm all local codes and CSA standards are met. They also have to record utility readings, test results, and the installation plans. Proper documentation is crucial for troubleshooting purposes, maintenance, and any future audits. And moving on, we have operational qualification. So OQ confirms the sterilizer can meet the conditions needed to sterilize. So for example, 132 degrees Celsius for 4 minutes, uh, and done after installation, then annually or after major services or repairs. It includes measuring heat up times, verifying sensor readings, comparing results to manufacturer tolerances. OQ must be successful before performance qualification begins. So requalification testing must be performed after, there were major component repairs. So let's say valves or controls were changed, or there's been construction or relocation. So if you were to look at this picture, this was actually Mount Sinai after they had major construction. So this was when they had new sterilizers up and everything. So they had to go through this whole process to ensure that the hospital MDRD meets regulations and standards. Um, Aside from that, yeah, requalification testing must be done. For example, when steam delivery has been changed, so you have to test for the pressure fluctuation, or you also have to check it if there was a cycle failure or any unusual outcomes. So let's say you got a printout that said it was successful, but when you take a proper look at the exposure time or the pressure, and it doesn't, like, those don't meet standards, then that means there's an issue with the sterilizer and they have to repeat the whole process again. So these steps prevent using a faulty sterilizer that might compromise sterility. So operational qualification, testing procedure. So technicians simulate typical cycles with test loads. Parameters like time, temperature, pressure are logged digitally or via chart recorders. All results must fall within manufacturer designed defined ranges. So like I said earlier, um, the pressure, temperature, all of that, they have to meet the actual successful cycle parameters. Even if the machine were to say it's successful, if you find any discrepancies, then you have to immediately log that and let the technicians of the manufacturers know so they could fix it once more. So results are reviewed and verified before moving on to the next step. So performance qualification or PQ. This part confirms that the sterilization works for real items under regular conditions. This is where we test wrapped instruments, sets, and packaging types used in practice. So it validates the entire process, not just machine function. Without passing a performance qualification, the sterilizer cannot be released for routine use. So some routine monitoring is daily checks ensure every cycle meets set parameters. So this includes reviewing physical printouts, verifying chemical indicators change colors, for example, logging results in a tracking system. Routine monitoring helps catch issues early and supports patient safety and regulatory compliance. So there are different types of sterilization process indicators, and we've talked about physical indicators and biological indicators in detail before. So physical indicators include readouts, so that's printouts that come out of the sterilizers, and it includes time, temperature, pressure, and it's good for machine performance tracking. We have chemical indicators. So these are color changing indicators. So it's like tapes or strips, and it shows exposure to certain sterilization conditions. It's quick and visible, but don't exactly confirm microbial kill. It doesn't really confirm that an item is completely sterile because if an item still has debris on it that a technician did not see, then obviously it's not sterile, even if it passes the sterilization parameters. And then we have biological indicators, so spore-based tests to confirm microbial kill. So that's the Geobacillus stereothermophilus. It's the slowest method, but it's actually the most reliable method. So each of these indicators have strengths and weaknesses. When used together, they create a full assurance system. So for physical monitoring, operators must be able to read and interpret charts or digital printouts properly. They must be able to identify any abnormalities on the printout, so a lower temperature than normal, for example. They must be knowledgeable in documenting results accurately and reporting any failed cycles and stopping the use of um, the sterilizer if it failed. So this is the front line safeguard in MDRD sterilization workflows. So if you guys remember, the operator responsibilities for physical monitoring. After every sterilization cycle, operators must check the printout before unloading items. You must look for temperature, time, and pressure. If applicable, it depends on the sterilizer you're using to make sure the cycle met all required parameters. It's a best practice to circle or highlight key values and then initial and date the printout. So if you were to look at the exposure times and minimum temperatures for steam sterilization on a printout, you would circle it, and it most likely will say 275 degrees Celsius. That is the maximum temperature that any steam sterilizer can meet. So these printouts are actually permanent records. They're required for compliance with standards like CSA Z314 and can be reviewed during audits or investigations. If anything is missing or out of range, the load is considered non-sterile and cannot be released. This step is essential for patient safety and legal traceability, so operators cannot skip it. All right, so now another testing that we do in MDRD is called the Bowie-Dick test. So it's required daily before using pre-vacuum steam sterilizers. It detects trapped air, which can prevent sterilization. It must be ran empty, so no load should be in there with a commercial test pack like this, for example. Results must be clearly readable and consistent. A failed test means the machine is out of service until a technician comes in and resolves what the issue is. So there's no there this one is definitely a fail. Even if you see that there's parts of it were black, it's definitely a fail. The whole thing must change to black in order to pass. So it's not similar to a chemical indicator like this. So for this one to be considered successful, it just has to pass this line, right? So even if it stops here, like the black line color change stops here, it still passes. But for this one, the whole indicator has to be changed in color. So the pack should be placed flat near the front bottom shelf over the drain. This area is most likely to trap air because it is next to the drain. Consistent placement ensures consistent test results. You have to still follow your department's standard operating procedure and manufacturer instructions. And this video here will show a more detailed example of how to properly place a Bowie-Dick test pack. So which steam sterilization cycle does not require the Bowie-Dick test? And it is actually both gravity displacement and steam flush pressure pulse. So for gravity displacement, the gravity cycle removes air by displacement. So it uses steam pressure to push air out, not vacuum. Since it does not rely on a vacuum system, there's no need to test the vacuum efficiency or its air removal performance, which is what the Bowie-Dick test does. As for the SFPP, the test is designed to evaluate vacuum performance, as we said, which SFPP does not use. Cycles that use SFPP remove air effectively, but via a different mechanism. So it uses steam and pressure pulses to slowly push the air out, right, to overtake the air inside the chamber. Meanwhile, the pre-vacuum, before any cycles, it actively removes air inside the chamber. So that's what this test is for. It's also called the air removal test. And then we also have what we call leak testing. This one is done weekly, like instead of every day. So leak testing checks if the vacuum chamber holds any pressure. Slow leak can allow air in, which compromises sterilization. So this is done weekly, usually before the start of a week. So it could be done on a Sunday night shift or a Monday morning shift. So larger leaks must be fixed before the sterilizer can be used. So if there was a failure during the leak test, that means a technician must be called in again to ensure that all is working in the system. So in comparison, Bowie-Dick checks air removal and steam penetration. So a common question you would ask during the Bowie-Dick test is, oh, can the sterilizer remove air and let steam in properly? Meanwhile, during a leak test, it checks for vacuum leaks in the sterilizer. So is the sterilizer's vacuum system sealed tightly enough to not let air or steam out? So that's what the whole system for leak testing is for. So moving on to chemical indicators. So chemical indicators are visual tools that confirm exposure to sterilizing conditions. They change color when exposed to a specific temperature or a chemical exposure. They don't really confirm sterility, but they provide quick feedback that helps staff assess whether a package should move to the next step. So how should internal chemical indicators be placed? Inside each package in a visible spot to verify sterilant penetration, taped outside each package with autoclave tape on each level of multi-layer sets, or A and C. And so, yeah, it's A and C. So you always place internal indicators inside the deepest part of each package, not necessarily underneath tray liners, as a lot of the students believed once. It has to be placed on top of the tray liners and at each level of a multi-layer set. This helps confirm the sterilant reach all internal surfaces. External indicators like autoclave tape, not to be mistaken with the instrument identification autoclave tape, it's this one. They don't provide this level of verification. So these are the types, class types and functions and some examples that are provided. So chemical indicators, like I said, are color changing tools that helps us confirm if sterilization conditions were met. They're divided into 6 classes based on how many parameters they measure and their intended use. So class 1 are the process indicators. So they're used outside packages, so autoclave tape like this one. They show exposure but not internal conditions. Class 2, which is the special test indicators. They're used for tests like the Bowie-Dick test to check vacuum and steam penetration. These are not used on instruments. So a lot of the time, the loads are empty when you do these kind of tests. And then we also have the single parameter indicators. These ones are not used in hospitals often. They're just not very efficient because all they do is measure one parameter. So a parameter in a steam sterilizer, maybe we have a tape that measures only temperature. So it ensures that we reach a certain temperature threshold or it reaches a certain steam exposure threshold. So it's not very efficient. So we actually rarely use class 3 indicators in hospitals. It's probably more used in research labs or manufacturers that are testing certain conditions in some sterilizers or other machines that they're coming up with. So class 4 is called the multi-parameter indicator. So it reacts to 2 or more parameter conditions. So for example, instead of just temperature or chemical exposure, it reacts to both of them. So chemical exposure and temperature, and maybe even time and temperature. It offers better internal assurance, but it's still not as good compared to 5 and 6, which we'll get into. So class 5 is considered the integrating indicator since it reacts to all sterilization parameters of that certain sterilizer it's being used on. So it's considered closest to biological indicators. It's still not as good as biological indicators, but it's good enough that this is what we use to ensure that the package was sterilized or at least met the sterilization conditions. So this is the one that most nurses will actually see whenever they open packages prior to surgical procedures. And then the class 6 one are called indicators. So these are very cycle specific. So they're very sensitive and are used to match a specific cycle's exact settings. So as an example, we all know that implant instruments, they go through longer cycles than regular instrument cycles. So maybe as an example, we would have a class 6 indicator that ensures that an implant cycle meets all of its sterilization parameters. So instead of the usual, 50-minute for a regular steam cycle for instruments, it goes up to an hour, 20 minutes, for example. So using a combination of these chemical indicator types, especially class 5 or 6 inside challenging loads, it helps ensure reliable sterilization. So chemical indicator limitations. So even if an indicator changes color, the item might still not be sterile due to incomplete cleaning, improper loading, or sterilizer malfunction. So you should never use chemical indicators as a substitution for proper, pre-cleaning, decontamination, cleaning, or biological indicator testing. So use of type 5 and type 6 chemical indicators. So typically the indicators will let you know what type they are. So this one is a type 5, this one is a type 6. Type 5 integrators respond to all sterilization parameters and are a strong assurance tool, while the emulating integrators like type 6 respond to a specific cycle and provide the most sensitive feedback. So these are used inside complex instrument packs to confirm sterilant reached all surfaces. But really, the most used one is type 5. It's all we really need in order to confirm that the cycle met all parameters successfully. So external chemical indicators, like we said, these include autoclave tapes, which are used on the outside packages, such as this. So even some peel packs actually have external chemical indicators. I didn't have a picture for it, but no. I will probably show it in class just to have an example. But all kinds of sterilization methods actually have different kinds of autoclave tapes that you use. So a typical one is this one, which is the steam. And this one, as you see here, is used for STERRAD. So this will successfully react to hydrogen peroxide sterilization methods. You can't, you know, use them interchangeably. So this one has to stay within a STERRAD, maybe even a vPro system. This one cannot be used as a substitute for this method. It just won't work. It will not react at all. It will not change colors. So next up is the sterility assurance summary. So effective sterilization requires a combination of equipment validation, IQ, OQ, PQ, so we went over it, routine monitoring, so those are daily or weekly tests, and of course the use of indicators, both all chemical, physical, and biological. So each step reduces the risk of releasing non-sterile instruments and ensures patient safety. And so now we'll be talking about the test number 1, details and review. I believe we only have 2 short answers questions, but the whole short answer section is worth 10 marks. So Both questions will be worth a lot of points as a result. The rest of it, it's just going to be the typical, format that I use. We'll have, I believe, 10 true or false statements. We will have 10 fill in the blanks, 10 multiple choice questions. There will be no diagrams or anything like that, so you don't have to worry about that. But yeah, we have 10 true or false, 10 fill in the blanks, 10 multiple choice, and two short answer questions that are actually worth quite a lot. So overall, the question is worth 40 marks, and we have 32 questions. I will go over the test number one review. Uh, Perhaps Friday, not anytime soon, because I want you guys to actually, make the effort to study it and go over it yourselves instead of just watching me give you the answers. I think it's better that way. But anyways, that's all for today. It was fairly short, I think. If you have any questions or concerns, just email me in this email here. And I'll see you guys next Sunday for your test. All right, bye bye.